Let me explain that how peak intensity in XRD spectrum depends on atoms positions. Here we have two unit cells, orthorhombic unit cells, and both unit cells have same number of atoms. This one is basically the base centered orthorhombic unit cell, and this one is the body centered orthorhombic unit cell. We know that each unit cell having two atoms per unit cell. One atom is basically from the corner and one atom is basically from the base. This atom is for another unit cell. So two atoms per unit cell. If you look into the body centered unit cell, also one atom from the corner and one atom from the body. So two atoms per unit cells. But we will see now that from base centered orthorhombic unit cells, we will get the diffraction peak, the intensity, and from body centered orthorhombic unit cell we will not get the peak intensity. We know peak intensity is very important parameter in XRD peak shapes. Peak intensity basically refer to the area under the curve. When we zoom this, when we magnify, so the area under the curve is basically called peak intensity. Let me explain in detail that how intensity depends on the atomic positions. This one is basically the base orthorhombic unit cell, and this one is the body orthorhombic unit cell. These are basically the lattices of this unit cell, and these are basically the lattices of these unit cells. We know that we get diffraction, we get the peaks only and only if the reflected rays satisfy the Braggs law. This is the Braggs law. You see here. So this is basically the lattices here of this unit cell, the base unit cell. So this is ray 1 here, this is ray 2. When this ray 1 strike on this atomic plane, the ray reflected here. Similarly, ray 2 reflected from. This is basically, let's suppose we have 001 plane. Right? We are only talking about this particular plane. So if you look here at these rays here, so these rays here, the reflected ray, both rays have here in phases here. You see here, both rays here and phases here. This means that this ray 2 basically cover extra path, that is basically called ABC, the path length, and it is equal to one wavelength here. So this means that it satisfied the Braggs law, and we will get peak here in the diffraction pattern here. This is the intensity. We will get the peak here. Now look here. This is the body's centered orthorhombic unit cell, and this is the lattices here. Ray 1 is basically, this is ray 1, this is ray 2. It is just like this base here. This ray 1 and ray 2 basically gives the constructive interference, in both are basically in phases here. This means that this ABC, the path length, is again equal to the wavelength. So Braggs law satisfied. But look here, for that particular plane, there is another body atom here. So this ray 3, when this ray 3 is just strike the atomic planes, and here it is basically out of phase here. It is basically out of phase, and the path difference is basically, what is the path difference? The DEF. The DEF is equal to half wavelength. So we don't get the diffraction in this case. So this is why for this particular plane, the diffraction peak is appear here in this base centered orthorhombic unit cell, while for this body centered orthorhombic unit cell, the reflection from that particular plane is disappear. This is how the intensity depends on the atomic positions.